Section 25 of Gray's Anatomy, Part 2. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recorded by Laurie Ann Walden. Anatomy of the Human Body by Henry Gray, Part 2. Mechanics of Muscle. In studying the mechanical action of muscles, the individual muscle cannot always be treated as a single unit, since different parts of the same muscle may have entirely different actions, as with the pectoralis major, the deltoid, and the trapezius, where the nerve impulses control and stimulate different portions of the muscle in succession or at different times. Most muscles are, however, in a mechanical sense, units. But in either case, the muscle fibers constitute the elementary motor elements. The direction of the muscle pull. In those muscles where the fibers always run in a straight line from origin to insertion in all positions of the joint, a straight line joining the middle of the surface of origin with the middle of the insertion surface will give the direction of the pull. If, however, the muscle or its tendon is bent out of a straight line by a bony process or ligament so that it runs over a pulley-like arrangement, the direction of the muscle pull is naturally bent out of line. The direction of the pull in such cases is from the middle point of insertion to the middle point of the pulley where the muscle or tendon is bent. Muscles, or tendons of muscles, which pass over more than one joint, and pass through more than one pulley, may be resolved, so far as the direction of the pull is concerned, into two or more units or single joint muscles. The tendons of the flexor profundus digitorum, for example, pass through several pulleys formed by fibrous sheaths. The direction of the pull is different for each joint, and varies for each joint according to the position of the bones. The direction is determined in each case, however, by a straight line between the centers of the pulleys on either side of the joint. The direction of the pull in any of the segments would not be altered by any change in the position or origin of the muscle belly above the proximal pulley. The action of the muscle pull on the tendon. Where the muscle fibers are parallel, or nearly parallel, to the direction of the tendon, the entire strength of the muscle contraction acts in the direction of the tendon. In pinnate muscles, however, only a portion of the strength of contraction is efficient in the direction of the tendon, since a portion of the pull would tend to draw the tendon to one side. This is mostly annulled by pressure of surrounding parts. In bipinnate muscles this lateral pull is counterbalanced. If, for example, the muscle fibers are inserted into the tendon at an angle of 60 degrees, it is easy to determine by the parallelogram of forces that the strength of the pull along the direction of the tendon is equal to 1/2 the muscle pull. Capital T equals tendon, M equals strength and direction of muscle pull, small t equals component acting in the direction of the tendon, phi equals angle of insertion of muscle fibers into tendon. Cosine phi equals small t divided by m, cosine angle 60 degrees equals 0.5. 0.5 equals small t over m, t equals 1/2 m. If phi equals 72 degrees 30 minutes, cosine equals 1/3. If phi equals 41 degrees 20 minutes, cosine equals 3/4. If phi equals 90 degrees, cosine equals 0. If phi equals 0 degrees, cosine equals 1. The more acute the angle phi, that is, the smaller the angle, the greater the component acting in the direction of the tendon pull. At 41 degrees 20 minutes, 3/4 of the pull would be exerted in the direction of the tendon, and at 0 degrees the entire strength. On the other hand, the greater the angle, the smaller the tendon component. At 72 degrees 30 minutes, 1/3 the muscle strength would act in the direction of the tendon, and at 90 degrees the tendon component would be nil. The strength of muscles. The strength of a muscle depends upon the number of fibers in what is known as the physiological cross-section. That is, a section which passes through practically all of the fibers. In a muscle with parallel or nearly parallel fibers which have the same direction as the tendon, this corresponds to the anatomical cross-section. But in unipinnate and bipinnate muscles the physiological cross-section may be nearly at right angles to the anatomical cross-section. Since Huber has shown that muscle fibers in a single fasciculus of a given muscle vary greatly in length, in some fasciculi from 9 mm to 30.4 mm, it is unlikely that the physiological cross-section will pass through all the fibers. Estimates have been made of the strength of muscles, and it is probable that coarse-fibred muscles are somewhat stronger per square centimeter of physiological cross-section than are the fine-fibred muscles. Fick estimates the average strength as about 10 kilograms per square centimeter. This is known as the absolute muscle strength. The total strength of a muscle would be equal to the number of square centimeters in its physiological cross-section times 10 kilograms. The work accomplished by muscles. For practical uses, this should be expressed in kilogram meters. In order to reckon the amount of work which a muscle can perform under the most favorable conditions, it is necessary to know 1. Its physiological cross-section, 2. The maximum shortening, and 3. The position of the joint when the latter is obtained. Work equals lifted weight times height through which the weight is lifted, or work equals tension times distance. Tension equals physiological cross-section times absolute muscle strength. If a muscle has a physiological cross-section of 5 square centimeters, its tension strength equals 5 times 10, or 50 kilograms. If it shortens 5 centimeters, the work equals 50 times 0.05 equals 2.5 kilogram meters. If one determines then the physiological cross-section and multiplies the absolute muscle strength, 10 kilograms, by this, the amount of tension is easily obtained. Then one must determine only the amount of shortening of the muscle for any particular position of the joint, in order to determine the amount of work the muscle can do, since work equals tension times distance. The tension of a muscle is, however, not constant during the course of contraction, but is continually decreasing during contraction. It is at a maximum at the beginning, and gradually decreases. This can be illustrated by the work diagram. AMD ordinate equals tension. AVX abscissa equals shortening. AD equals tension of muscle in extended or antagonistic position. AV equals amount of actual shortening. AM equals tension in mid-position equals absolute muscle strength. dV shows how the tension sinks from maximum in the extended position of the muscle, where it is about double that in the mid-position, M, to nothing on complete contraction. Delta AdV equals work diagram. In reality, the hypotenuse is not straight, but has a concave curve. The delta has the same area as the rectangle AMM'(V). AM equals the average tension. Work equals AM times AV kilogram meters, if the size of the ordinate is expressed in kilograms and the abscissa in meters. Although the muscle works with a changing tension, yet the accomplishment is the same as if it were contracting with the tension of the mid-position. In reality, the amount of work is somewhat greater, since even in extreme contraction the muscle still retains a certain amount of tension, so that the maximum amount of work is more nearly like AdX. We know that a muscle may have an extreme actual shortening of about 80% of its length when the tendon of insertion is cut. The trapezoid ADSV represents more nearly the amount of work, but since there are only approximate values, and ADSV is not much larger than AM'V, we may use the latter. Only the tension and amount of shortening are needed to determine the amount of work of the muscle. Neither the lever arm nor the fiber angle in pinnate muscles need be considered. The diagram shows that the lever arm is of no importance for determining the amount of work the muscle performs. JB and JB1 equals 2 bones jointed at J. CD and EF equal the direction of the pull of 2 muscles of equal cross-section, each having a muscle tension of 1,000 grams. The centers of the attachments are such that perpendiculars J small c and J small e to CD and EF are equal to 40 and 23 millimeters respectively. J small c equals 40 millimeters, and J small e equals 23 millimeters. The static moments are equal to 1000 times 40 and 1000 times 23. Therefore the first muscle can hold a much larger load, L, on the bone JB1 at H1, 100 millimeters from J, than the second muscle whose load can be designated as L1. Equilibrium exists for the first muscle if L times 100 equals 1000 times 40, or L equals 1000 times 40 over 100 equals 400 grams. For the second muscle, L1 times 100 equals 1000 times 23. L1 equals 1000 times 23 over 100 equals 230 grams. If we suppose JB to be fixed and JB1 to move in the plane of the paper about J, and the muscle CD to shorten 5 millimeters, C small d equals CD minus 5 millimeters, and with the tension of 1000 grams, JB1 will take the position JB2, and the load, L, will be lifted from H1 to H2. If the second muscle likewise shortens 5 millimeters, then E small f equals EF minus 5 millimeters, and with the tension of 1000 grams, the bone, JB1, will take the position JB3, and the weight or load, L1, will be lifted from H1 to H3. The question now is to prove that the work done is the same in both cases, namely, 5 times 1000 gram millimeters. If so, 400 times H1 H2 equals 230 times H1 H3 equals 5000 gram millimeters. Since the two radii C small d and C small d prime are very long as compared with the arc small d d prime, we may consider this short arc as a line to CD at small d prime. Likewise the arc small f prime may be considered as a straight line to EF. In the same manner we can consider the short arcs f, d small d, H1 H2, and H1 H3 to the line JB1. The sides d small d prime and f small f prime of the delta d small d prime and f small f prime are each 5 millimeters. The lever arm DJ equals 60 millimeters, and JF equals 30 millimeters. The delta d prime is similar to the delta d small c j. Hence d small d to 5 is to 60 to 40. D small d equals 300 divided by 40. Also H1 H2 to d small d as to 100 to 60. H1 H2 to 300 over 40 as to 100 to 60. H1 H2 equals 300 divided by 24. Hence f small f to 5 is to 30 to 23. F small f equals 150 divided by 23. Also H1 H3 is to f small f as to 100 to 30. H1 H3 is to 150 over 23 as 100 to 30. H1 H3 equals 1500 over 69. 400 times 300 divided by 24 equals 230 times 1500 divided by 69 equals 5000. Thus we see that the work of the two muscles depends on the size of the contraction and on the tension, and not on the lever arm in very small contractions, or in the summation of such contractions, and therefore for large contractions. In the first muscle a large load is moved through a short distance, and in the second muscle a lighter load is moved through a greater distance. The amount of work accomplished by pinnate muscles is not dependent upon the angle of insertion of the muscle fibers into the tendon, as will be seen by the following diagram. T' equals direction of the tendon pull. WA equals direction of muscle fiber before contraction. M' equals direction of muscle fiber after contraction. V equals amount of contraction. M equals tension of the muscle. Phi equals angle of insertion of muscle fiber. T equals tendon component equals M times cosine phi equals the weight carried by the tendon to balance the muscle tension. D equals distance tendon is drawn up. 1. M times V equals work done by the muscle fiber. 2. T times D equals work done by the movement of the tendon. If we consider the distance V as being very short, then the line BC can be dealt with as though it were perpendicular to AC. Then V equals D times cosine phi, or D equals V over cosine phi. Since T equals M times cosine phi, or M equals T over cosine phi. M times V equals T over cosine phi times D times cosine phi equals T times D. If this is true for very minute contractions, it is likewise true for a series of such contraction, and hence for larger contractions. If we assume that phi equals 60 degrees, M equals 10 kilograms, and V equals 5 millimeters, the work done by the contracting muscle fiber equals mv, or 10 times 5 kilogram millimeters. Cosine angle 60 degrees equals 1/2, hence T equals 1/2 M, and D equals V over 1/2 equals 2V. 1/2 M equals 5 kilograms, and 2V equals 10 millimeters. Hence TD equals 50 kilogram millimeters, or the work done by the movement of the tendon in lifting the load of 5 kilograms a distance of 10 millimeters, and is exactly the same as that done by the muscle fiber. The load on the tendon is but 1/2 the tension of the muscle, but the distance through which the load is lifted is twice that of the amount of shortening of the muscle. If phi equals 41 degrees 20 minutes, then cosine phi equals 3/4. Hence T equals 3/4 M, and D equals 4/3 V, and TD equals MV. In pinnate muscles, then, we have the rather unexpected condition in which the same amount of movement of the tendon can be accomplished with less contraction of the muscle than in muscles where the fibers have the same direction as the tendon. The action of muscles on joints. If we consider now the action of a single muscle extending over a single joint, in which one bone is fixed and the other movable, we will find that muscle pull can be resolved into two components, a turning component, and a friction or pressure component, as shown in Fig. 369. dF equals the fixed bone from which the muscle takes its origin. dK equals the movable bone. OI equals a line from the middle of origin to the middle of insertion. IM equals size and direction of the muscle pull. If the parallelogram is constructed with IT and MB perpendicular to DK, then IT equals the turning component, and IB equals the component which acts against the joint. The size of the two components depends upon the insertion angle, phi. The smaller this angle, the smaller the turning component, and the nearer this angle phi is to 90 degrees, the larger the turning component. IT equals IM times sine phi. IB equals IM times cosine phi. If phi equals 90 degrees, cosine phi equals 0, sine phi equals 1, hence IB equals 0, and IT equals IM. If phi equals 0 degrees, cosine phi equals 1, sine phi equals 0, hence IB equals 1, and IT equals 0. With movements of the bone dk, the angle of insertion is continually changing, and hence the two components are changing in value. If, for example, the distance from origin O to the joint D is greater than from D to I, as in the brachialis or biceps muscles, the turning component increases until the insertion angle phi equals 90 degrees, which is the optimum angle for muscle action, while the pressure component gradually decreases. If the movement continues beyond this point, the turning component gradually decreases, and the pressure component changes into a component which tends to draw the two bones apart, and which gradually increases. When the bone DK is in such a position that the insertion angle phi equals 41 degrees 20 minutes, the pressure component equals 3/4 Im, and the turning component 1/4 Im. At 60 degrees the two components are equal. At 90 degrees the pressure component equals 0, and the turning component equals Im, and at 131 degrees 21 minutes the pressure component has been converted into a pulling component, equals 1/4 Im, and the turning component equals 3/4 Im. If, for example, the distance from the origin O to the joint D is less than the distance from the insertion I to the joint D, as in the brachioradialis muscle, the insertion angle increases with the flexion but never reaches 90 degrees. The turning component gradually increases to a certain point, and then slowly decreases as shown in Fig. 371, while the pressure component gradually decreases and then slowly increases. It always remains large, and its action is always in the direction of the joint. Levers. The majority of the muscles of the body act on bones as the power on levers. Levers of the 3 class are the most common, as the action of the biceps and the brachialis muscles on the forearm bones. Levers of the 1 class are found in movements of the head where the occipito-atlantal joint acts as the fulcrum and the muscles on the back of the neck as the power. Another common example is the foot, when one raises the body by contracting the gastrocnemius and soleus. Here the ankle joint acts as the fulcrum, and the pressure of the toes on the ground as the weight. This is frequently, though wrongly, considered a lever of the 2 class. If one were to stand on one's head with the legs up and with a weight on the plantar surface of the toes, it is easy to see that we would have a lever of the 1 class if the weight were raised by contraction of the gastrocnemius muscle. The confusion has arisen by not considering the fact that the fulcrum and the power in all 3 classes of levers must have a common basis of action, as shown in Fig. 372. If the fulcrum rests on the earth, the power must either directly or indirectly push from the earth, or be attached to the earth, either by gravity or otherwise, if it pulls toward the earth. If the power were attached to the weight, no lever action could be obtained. There are no levers of the 2 class represented in the body. End of section 25.